Hello, my name is Mayur. I'm going to give my presentation on paper titled Knowledge Transfer via Multimodal Local Structure Mapping. So my team name is Mayur underscore B. My roll number is 23M1027, and this work is done as part of IE 506 course project. So this is the outline. So we will start with introduction followed by transfer learning, then weighted ensembling, and we will end with references. So the researchers have mentioned their contribution, main contributions as locally weighted ensemble framework to address transfer learning. And the second main contribution that they have mentioned is approximating model weights using local manifold structures. So in order to understand the researchers' approach, I need to make myself familiar with the topics that I have listed here, which are transfer learning, weighted ensembling, locally weighted ensemble learning, Bayesian model averaging method, and locally weighted ensemble clustering. So starting with transfer learning. So transfer learning is very different from traditional machine learning, because in traditional machine learning we use different training data sets to train different machine learning models. But in transfer learning, we use one very big data set to train one machine learning model, and then we use the architecture of that machine learning model to train another machine learning model. So this process of applying the knowledge of a pre-trained model to develop another model is called as transfer learning. Transfer learning is very popular in the context of neural networks, because neural networks require huge amount of data to train the neural network, but the labeled data is very expensive. So transfer learning is applied in order to train the model using limited data. So it saves cost as well, and it saves time as well. So now we will see modes of using the pre-trained model in transfer learning. So as we saw in the previous slide, there are two modes of using pre-trained model in transfer learning. So in the first mode, initial layers are frozen and last few layers in the network are retrained. So as you see in figure 2, which shows the neural network called AlexNet, we will first remove the output layer, and then we will freeze the initial layers, and we will pass our limited training data only through some of the outer layers such as FC4096, because of which the weights of the features in the layers will get readjusted, which will result in a new machine learning model. In the second mode, the entire model is initialized with pre-trained weights, and the entire model is set to trainable mode. Basically, we again remove the output layer, and unlike mode 1, we now pass our data through all the layers, because of which the initial weights of the features will now get readjusted in all the layers, and we will get a new model. Now, depending on the amount of training data that we have, and the similarity of our training data with the data that was used to pre-train the model, we will decide whether should we choose mode 1 or mode 2. Now I would like to discuss locally weighted learning. In locally weighted learning, uh, in order to calculate the predicted value of a data point, we select few neighboring data points, and then we calculate the weight for those neighboring data points using a weight function, which in this case is 1 by d. Now, once I calculate the weight, now I will multiply the value of those weights with the actual value of those data points, and I will add them and finally get the predicted value of our initial data point. This process has been shown in figure 3. And if we follow this process for all the data points, we get a best fit line, which you can see in figure 4. Uh, the example, we can look at a very good example which has been shown in the slide for a point x equal to 42. So Uh, in the previous slide, the weight that we took was 1 by d. There are many other weight functions such as 1 by d square, 1 by d plus 1, e to the power minus d square. This method does not give very good results when we are dealing with many outliers. This method will not work if the data set is high dimensional. Now we will look at locally weighted ensemble learning for regression. Here, in ensemble learning, we combine different base models in order to make one final prediction. So, if you look at the objective function of this ensemble learning, which is equation A, f of x equals I equal to 1 to m wi f of I x. So here m represents the number of base models, wi represents the weight that has been given to each base model, and fix represents the output of each of those base models. If you look at figure 5, you will see the lowest layer consists of all the input data, the middle layer consists of all the base models, and each of the and the output of each of these base models have a weightage called wix. Now there's a now we get the value of this wix from Bayesian model averaging method. So this term wix comes from Bayesian model averaging method. So in Bayesian model averaging method, we have prior probability and we have posterior probability. Prior probability is the initial belief that we have about the likelihood of each model before taking into consideration some data D, and posterior probability is the same after taking into consideration some data D. Now if you look at equation A, it gives us posterior distribution of y, meaning the posterior probabilities of all the possible values of y given a data set D for a model mi. Now in this equation A, we have a term called py by x dmi, which gives us the posterior probability for every single value of y given a data set D and for a model mi. Now, if you look at the second term in the equation A, which is PMI dash D, it now it represents the posterior distribution of the model given data D. Here, if we simply replace D with X, then we get the function Wix equals PMI by X, which is shown in point 6. So this function can be used as a model weight or a weight function which is locally adjusted for x. So this is the same function that I showed in the previous slide, which is this slide, wix equals pmi by x. Now this weight function takes into consideration the local behaviors of the model at each test example. That is why this ensemble learning is called as locally weighted ensemble learning, and the models f1 f2 till fm are regression models, hence locally weighted ensemble learning for regression. Now let us discuss locally weighted ensemble clustering. So the entropy for a random variable x is given by equation A, in which p of x is the probability mass function. So entropy basically shows the uncertainty associated with a random variable. So if we have two clusters, cluster A and cluster B, and if the entropy of the random variable is high, that means we cannot be sure which cluster that random variable x will belong to. But if the entropy is low, then we can say for sure that the random variable x must belong to either cluster A or either cluster B. So if we have n discrete independent random variables x1, x2, x3, then their sum will be given by joint entropy, whose mathematical formula is given in equation B. Now, when it comes to ensemble clustering, we have many different base clusterings. So these base clusterings are very similar to the base models that we have seen in the previous slides. So in equation C, pi 1, pi 2, pi 3, etc. represent the base clusterings, and in equation C, capital M shows the number of base clusterings. Now within each base clustering, there are different set of clusters which are represented by C1m, C2m, C3m, etc. in equation D. Now let me show you the figure, which is this figure. So in figure 6, A, B and C represent different base clusterings, and within each base clustering you can see C1, C21, C31. Then in B you can see C12, C22, C32, which show different set of clusterings within base clusterings. Now if I want to calculate the uncertainty or entropy for the entire cluster Ci, instead of just one random variable x, then I have to use the equation A. So in equation A, P of CICJM is uh, basically shows the probability of the objects or the data points in a cluster CI belonging to another cluster CJ as well. For example, if the data points in cluster CI are also present in another cluster CJ, then the value of CI intersection CJ will be very high, which will result in very high values of uncertainty. And if the data points or the objects in CI only lie in CI, then the uncertainty of CI with respect to base clustering pi m will be very low. Okay, so this was so using equation A, we can calculate the entropy for the CI cluster. And if I want to calculate the entropy for the entire ensemble, then I basically add them up using the summation function, which is shown in equation C. So equation C will give us the entropy of the of all the base clusterings combined. So the final output is shown in figure 7. So I have taken this figure, this picture from the research paper that I have referred to. So these final values are used by a consensus function. This consensus function will then give us a final prediction value. Now consensus function is not a part of the my research paper, hence I am not discussing it. And in this slide, we have observations which I have already discussed in the previous slide. Now, I would like to discuss the data. So we have five different kinds of data. One is synthetic data and four are real data. So not much the details of the synthetic data have not been shared in the research paper, but they have shared the details of the four real data set. So out of which the first data set is ACM SIGKDD. Now this data set comes from a conference that was organized in 2006. So this data set basically contains messages which are spam messages and messages that are not spam. So it has 4,000 labeled examples in the training set and 2,500 test examples in the test set for each user. Now what the researchers did, that they used their algorithm in order to develop a personalized spam filtering method model for individual users. The link for the dataset is given in the slide. Now, in 20 newsgroup dataset basically contains 20 newsgroup documents partitioned across 20 different newsgroups. So basically, there are 20,000 20,000 text documents, and these text documents belong to 20 different categories. And again, the researchers have used their algorithm in order to develop a model that can categorize these text documents into 20 different categories. Then we have the Reuters 21578 dataset. This is again very similar to the previous model. Here we have thousands of financial news articles that belong to several categories. And again, the researchers have used the algorithm that they have developed in order to develop a model that can categorize these financial news articles, basically the text documents, into different categories. Now, the KDD Cup 99 dataset. So, KDD Cup 99 dataset basically has contains the data, the connection records from a local area network. And each of these connection record either belong to a normal category or an attack category. So also, this dataset contains, I think, 32 continuous features, out of which some of those features are host, service, and traffic features. Then, what the researchers have done is that they have again used their algorithm in order to develop a model which can categorize the connection records into normal or attack. So yes, the for dataset 1 and for dataset 3, I was not able to find any code, and I was not able to find original code. Also, I was not able to find a code in any other repository that could have been made by other people. But for dataset 2 and dataset 4, again, the original code that the researchers have used is not available. But there are some codes in Python that are available on GitHub repositories, whose links I have mentioned. So I have referred four main papers for this presentation whose links are listed, whose links are given in the slide. Uh, Thank you.